Hello, everybody. Welcome to the GEOTOP-A web seminar. It's my pleasure to introduce our speaker today, Sophia Knight from University of Minnesota Duluth in USA. And today, Sophia will talk to us about truth set algebras, a new way to prove undefinability. So please, Sophia, the stage is yours. Thank you very much.
Hey, thanks for inviting me. I'm happy to be here today. In this presentation, I'm going to talk about the definability and undefinability of logical connectives through one another. The way that we kind of came up with this method of proving undefinability results was that we were working on kind of a logic with AI applications with a multi-agent logic where different logics have different memory abilities. And we came up with some operators and tried to prove which ones were undefinable in terms of each other, which ones were necessary and unnecessary. And we eventually, with this little bit complicated logic, we came up with this undefinability method of proof that we call truth sets algebras, that's focused on closure and checking whether something is definable in terms of something else. So we realized that this method was applicable to a wide variety of logics and is kind of unifies different undefinability proof methods that have been used for different logics and systems historically. So today I actually won't go into the AI logic because it's a little bit complicated and long to explain, but instead I'm just going to talk about the truth set algebra method of proving undefinability. And I'm going to show you some classic results that were already proved using different methods, but some nice new proofs of them that you might like to see. And then a couple of results that we believe are new in three-valued logic. And if anybody has any questions at any time, I'm happy to answer those right away. I can see the chat or feel free to speak up. It's okay with me. So the logics that we're going to focus on today, can everybody see my screen correctly? Is everything good with that?
Yes,
I think the slides are okay, yes.
Good, good. So I'll talk about propositional logic, some well-known definability results, but just to introduce the truth set algebra method. Then I'll talk about some temporal computational logics and undefinability results for those. Then I'll get into classic intuitionistic logic results and some new undefinability proofs for results that were already known but were proved using different methods. And then if there's time, I'll get into three-valued logic a little bit and some infinitary temporal logic results. Propositional logic. So here are some examples of equivalences in propositional logic that show that many propositional logic operators are definable in terms of one another. It's well known, probably everybody here knows that in basic propositional logic, if you have negation and any other single operator, implication, conjunction, or disjunction, that's a sufficient set of operators, and you can define all the other operators based on those, even two-way implication, obviously. So these first six results, these are really well known. One of the first things you learn in propositional logic. And then this blue result, I think is a little bit less well known, clearly true as soon as you see it, but if I just ask somebody, is disjunction definable in terms of implication? I don't think most people know that off the top of their head. And of course, in propositional logic, there's a connection between disjunction and conjunction. We think of them as symmetrical operators, somehow very closely related. So when we see that disjunction is definable in terms of implication, we may wonder, is conjunction also definable in terms of implication? If the answer is yes, then you would know how to set up that proof, right? But if I tell you the answer is no, it's going to be a little bit tricky to prove that. You're going to have to think, how do we prove this? What proof method do we use here? So this is going to be our first example of a truth set algebra proof. So actually, even though or is definable in terms of implication, and is not definable in terms of implication alone. To prove this, we use truth set diagrams. So here is a truth set diagram for and. So it's basically the same thing as a truth table, you see. So we have Q and we have P, and this tells us the truth value of P and Q under all possible valuations, because a valuation is a model for propositional logic. So then here's how we define a truth set algebra. So this is the truth set algebra for implication. This is a closed set of formulas under implication. So we start with P and Q, and this table shows us the truth set diagram for phi, which is in the left-hand column, implies psi, which is in the top row. So here's P implies P, and black is true, white is false. Here's P implies P, here's P implies Q. So we start with P and Q, and we get these four diagrams. And these give us three different new things to add to our table. So we add this one here. We label it P or Q because that's we add this one here, P implies Q. The order in the table is just kind of for graphical purposes, but we add Q implies P here and true here. We just call it true because that's the shortest name for that formula. And then we take the closures of those under implication, and we only end up adding one new thing, which is here. And so we add that to our table. And once we have added that, those 6 formulas are the only formulas that we can obtain by implication, starting from P and Q. So this means no matter how complicated we make our formula, how many implications we add between different versions of these, any formula we obtain will be equivalent to one of these 6 formulas because it's a closed set. So then this lets us answer the question of whether conjunction is definable in terms of implication. So we see that this truth table, this diagram does not show up anywhere in this closed truth set algebra. And that means there's no way to obtain a formula equivalent to P and Q using just implication. So this is not difficult to understand. This is fairly obviously true, but we can extend this method to other logics to prove more complicated undefinability results. Any questions so far? Is this okay for everybody? Okay, so I will get into how to extend this to other logics. So that's the theorem that we just proved using the truth set diagram, that nice graphical proof. Now I'm going to talk about temporal logic. Temporal logic is commonly used in computer science. I don't know if everybody here has seen it or not. So we're going to talk about linear temporal logic today. And I'll give a brief overview of what linear temporal logic is, and then I will prove some undefinability results. So this is our syntax for temporal logic. We have basic propositional operators, and then we have what are called temporal operators. I'll show you the semantics for those in a second. So LTL, linear temporal logic, the models are just a number line. So numbers from 0 up to infinity, they're infinite models, but just a single line, which is why it's called linear. And then our valuation just assigns each number what propositions are true at that number or not. So before I get into the semantics, let me show you what these models look like. Here's a little example of a model. This goes from 0 through 10, but then it goes on from there. It's just not in the picture. And our proposition is just a sun, only true at number 4, no propositions true anywhere else. So this is the kind of model that we're describing. So now I can explain the semantics to you. The propositions are just true at certain numbers where they're defined. Negation and or work the way that you would expect. And then here are our interesting temporal operators. So F captures the idea of finally, or we might say eventually. So at a number, F phi is true if phi is true at some greater number. So if phi is true sometime in the future, then F phi is true now. G captures the notion of globally. Also, we could say from now on. So G phi is true if for all the numbers greater than n, the number we're at now, phi is true. And that includes n. So we say phi is true globally if phi is true now and at all future times. X stands for next, and it just means it's true at the next time step, n+1. U stands for until, it's a binary operator. So this says phi until psi. So it says psi is true at some time in the future, and from now until psi is true, phi is always true. So I'll just show you a picture of that real quick. Here's a picture of red until blue at 0. So red is true now, and every time step until blue is true. And then we also have another version of until called weak until. And this says if phi is not true at some time in the future, then psi must be true at some time in the future, and phi must be true at all the time points until psi is true. So this turns out to mean either phi is always true or phi is true until psi is true, and then we don't care what happens after psi becomes true. Now this logic is used for talking about properties of computations. For example, it would be useful to know that the system never reaches deadlock, so that would be not F deadlock, something like that. You can express fairness properties as well, like if a request is made, then the request remains in the queue until it is answered, something like that, those kind of properties. And LTL has a lot of practical applications. It's been used to verify airline software and things like that. So here's a couple examples just in case people haven't seen LTL before. So this is M1. The only proposition is the sun, which is true at state 4. So 0 makes F sun true. 4 also makes F sun true because now is part of the future, but 5 does not make F sun true. This is M2. Red is our proposition, and every state is red. So this model makes G of red true for any n. So 0 makes G of red true, 5 makes G of red true, and so on. This is M3. I showed you this one already because until is a little bit difficult to just read from the semantics. So again, 0 makes red until blue true. 1, 2, 3, and 4 all also make red until blue true. Also, red is weakly until blue true. And then if we are looking at weak until to understand the difference between until and weak until, in M3, red until blue is true and red weakly until blue is true. In M2, red weakly until blue is true because we count red staying true forever as being part of weakly until, but red until blue strictly is not true. So that's just a little overview of LTL. Our basic modalities are F, which is eventually G, globally always, until, and weakly until, and next. So we have 5 operators. So there's some definability results that are well known for LTL. Unsurprisingly, eventually and always are De Morgan duals of each other. So you only need one of those 2 operators. But you can also define eventually or finally in terms of strong until. So F phi is equivalent to true until phi. If you look at the semantics, it's clear that that's true because true always holds. And this just means something has to be true and phi has to eventually happen. If you only have weak until, then eventually phi is the same as saying phi is false until weakly until false is true. Since false never happens, that just means phi is eventually true. And you can define strong until in terms of eventually and weak until, which intuitively makes sense. And same thing, weak until is just either phi is always true or phi is true until psi is true. So you only need one of the strong and weak untils if you have a temporal operator. So these are definability results, standard. But then this raises the question of what about undefinability results? What operators do we actually need? What operators are not expressible in terms of one another? So the truth sets of these formulas, rather than truth tables, they're sets of numbers. They're the points in a model where the formula is true. And we consider formulas to be semantically equivalent if they both have the same truth sets in all models. So we're going to prove that weak until and strong until are both undefinable through any formula without x, u, or w. So we're going to show that you can't define until or weak until without, or in terms of only f and g, basically. So we're going to build a specific model, and we're going to show that the truth set of until and the truth set of weak until is not definable in terms of the truth sets of the other operators by building a set that's closed under the other operators. So our model is going to make p true at all the odd numbers, and it's going to make q true at all the numbers divisible by 4. I'll show you a picture of the model now. Okay, so this is actually the truth set algebra, but and again, black is true, white is false. So you see the truth set for p here, all the odd numbers, we count from 0. And the truth set of q is here, all the numbers divisible by 4. So we first take all the Boolean combinations of p and q. Booleans work the same way as always in LTL. And then we're interested in checking whether until and weak until are definable in terms of f and g. F and g are actually interdefinable equivalent, so we're just going to use f. So we are going to take the f operator applied to all these Boolean combinations of p and q. Remember, f means eventually. So since everything is kind of repetitive, recurring, if it's ever true, then it's going to be, the f of it is just going to be always true, right? Because it's recurring forever, and there's some point in the future where it's true. So since p and q sort of have separate spots, they're not opposites of each other, f of any Boolean combination of p and q is just always going to be true, because there's always going to be some point in the future where some of those combinations of p and q is true. So this is just like universal truth. And then we also have false, where p and q are both, or this is just false by itself, actually, the constant. And f of false is also false, because nothing is ever true. Whoops. So this is the truth set algebra for all the combinations of p and q and f and g. And then here is the truth set algebra for p until q. So if we think about p until q, remember it means p stays true until q is true. So in this specific model, that's going to be just the points either where q is true right now, or where p is true directly before q is true, since p sort of alternates. So it's basically like 3, 4, 7, 8, and all those numbers, like number divisible by 4 and then odd number before it. So it's this picture here. So that's p until q. P weakly until q is the same in this case. Since p is not true forever, p until q and p weakly until q are true at exactly the same states. Neither of those shows up in this closed truth set algebra. So that's a proof that until and weak until cannot be proven using f, g, and Booleans. That was proved in a paper in the 90s, but a different, sort of more complicated proof. So this is a nice application of the truth set algebra technique. Any questions about anything so far? Okay, so I said this out loud, but here's our lemma that if you apply f to any of these truth sets, you get either true or false. And then that u and w are not definable in terms of these other formulas. So there's the formal theorem, and yeah, it was proved in 2002, 95. Okay, so now I'm going to talk about intuitionistic logic. I guess everybody here has probably seen some amount of intuitionistic logic somewhere before. So I'll just give a brief overview of it. So intuitionistic logic uses the same operators as propositional logic, but it's a constructive logic. So it's defined through a proof system, not definable through finite truth tables. And its idea is to be more constructive than propositional logic. So you do not have the law of excluded middle, and implication behaves a little bit differently than in propositional logic. So what's less well known than maybe basic intuitionistic logic is that you can give a semantics of intuitionistic logic based on Kripke structures. So an intuitionistic Kripke model is a relational structure. So you have a set of worlds. I believe it's always a finite set, if I'm right about that. And there's a partial order on your set. And then the important thing is that the truth set for each proposition has to be upward closed. So if P is true at a state W and W is related to U, then P has to be true at state U also. So obviously that ends up being transitive. And if P is true at W, P is true at all states that are above W. So if you use this structure, you can define the semantics like this for intuitionistic logic, and you get exactly the same intuitionistic truths as you do with any other system of intuitionistic logic, proof system or semantics. So propositions are just defined point by point at the points where they're true. Negation, though, is defined in a new way. So we don't just say phi is false, not phi is true at W if phi is not true at W. Instead, we say not phi is true at W if for every world above W, transitively closed, phi is not true. And it's important to keep in mind here that's different than the negation of phi being true. I'm just saying that there's no world above W that satisfies phi. And is defined as usual, or is defined the normal way. We don't have De Morgan's law anymore in intuitionistic logic. And so we need both of these operators. And then implication is also defined in a new way. So implication, we say that, so we're at W now. And if we look at any world U that's above W, then any world that's above W, if phi is true there, then psi has to be true there. So it's like we look at the whole set of worlds above W, the world we're at now, and check whether all the ones that make phi true also make psi true, including W itself. So if you use this semantics to check what formulas are true and false at W, you get the same universally true formulas as with other semantics or proof systems for intuitionistic logic. Truth set is just defined as the set of all points that make a formula true. And semantic equivalence is defined as being true at the same points as usual. Okay, so now I will show you a little example of how we can use this method to prove undefinability results. So our first result is going to be to prove that we cannot define if P then Q in terms of our other operators in intuitionistic logic. So here we have, we picked two basic formulas, P and Q, for this proof. So P is true at the top two states plus the lower right-hand state. Q is just true at the top two states. And here's our OR diagram. OR is just kind of union as usual. And then here is our negation diagram for our basic formulas that we can build using OR. So, and remember, negation is not just complement. Now negation kind of looks at all the sets that are above and checks whether it's true, whether a formula is true there. So, for example, like not phi ends up being false everywhere, because if you look at the bottom state, there's a state above it where phi is not true, right? And if you look at this state, it's not true there, so that automatically makes not phi true there. And then this state, we actually flip the truth value because we're not looking at the states above because it's at the top, and so on. So we look at all these, and then we look at our diagram for if P then Q. Let's go back to our semantics for if P then Q again. Here's our semantics for if P then Q. So it's that we have to look at all the worlds that are above it, and if they make P true, then they have to make Q true. So we check that here. And all the worlds above. So this state's the only interesting one, this little kind of left-hand corner state. All the worlds above it that make P true also make Q true. So these are the set of states where if P then Q is true. This does not show up anywhere in our truth set diagram. So that tells us that if P then Q is undefinable through the other operators. And so this is a little bit more complicated result. We do have to pick a special value of P and Q rather than looking at all the possibilities like we do with truth tables. But once we find that value of P and Q, then this proof is pretty mechanical and automatic. But I think it's important to emphasize here, this isn't just an exhaustive search method. With basic propositional logic, it does end up being an exhaustive search method, but with more complicated logics, we actually have to find the right specific basic propositions so that when we build up our truth set algebra that's closed under all of our other operators, we get a closed truth set algebra that does not include the operator that's undefinable, if that makes sense. And here's the formal lemmas and the final theorem, which I already explained to you. And then here's another intuitionistic logic result. So the formula not P is not equivalent to any formula that doesn't use negation. This actually needs to be, you can prove this with monotonicity. This is another result that has different proofs, but this is nice to fit it into the same framework as all these other undefinability results. So we just see that all we have to do here is use one formula P. We pick this one because it works. We got P and true. And we use implication to combine them. Does not give us our not P result. And we can prove that or is undefinable without or. So here we have our truth set algebra for implication. Here we have our truth set algebra for negation. And we're actually taking the closure of the union of these two sets. So we have all our OR formulas, and then our negation formulas don't change that. So, and then here's our P or Q formula. Does not show up anywhere in the rest of our algebra, which is the result of applying all the other operators. So we prove that P or Q is undefinable in terms of negation and implication. And again, we had to pick a specific P and Q to make this proof work, different from the P and Q we used in the earlier proof. Then our last theorem for intuitionistic logic is that we can't define and through implication and negation. So for this one, we have to pick a new basic set of propositions, P and Q. They're both true at the top states. P is kind of true at the left-hand state, and Q is true at the right-hand state. That gives us actually 5 possible formulas that we can build up using implication. Negation does not take us out of that set, keeps us in that same set, so we're still closed. So these are all the models you can build using negation and implication, starting from these P and Qs. And then obviously P and Q, remember, and is just the same as intersection, even in these models. So P and Q gives us this model, which is not definable through the other operators, as we see through the chart. So we just have some really simple, nice proofs of some classic results in intuitionistic logic that have been proven in different ways in the past, but This is nice and uniform and simple. And these results, they were proved in the 30s, but using really different techniques, I think based on topological models. And our proof does rely on the completeness with respect to Kripke semantics, which was proved later. So it's not like McKenzie and Tarski had access to this method exactly. Okay, yeah, we have a little bit of time left. So maybe this is my favorite part of this talk. We're going to do some results in 3-valued logic. And I think these might be new results. I haven't found them anywhere else at least. So 3-valued logic is a logic where formulas can be true or false or something else. That something else may have different meanings based on the applications we have in mind. It might mean undefined, it might mean uncertain. I don't know what else it means, but possibly other things as well. So again, white is false, black is true, and then X is the other option. So and or, there's really only one way to define them. That makes sense, kind of an extension of binary logic and or. But implication, there are 2 different reasonable ways to define implication in this 3-valued system. So Lukasiewicz worked on 3-valued logic, I think maybe first, and then Kleene had a different notion of implication that he used in 3-valued logic. So Lukasiewicz's logic, basically, any truth value implies itself, that gives you true. So uncertain implies uncertain, that's true in Lukasiewicz logic. In Kripke or Kleene semantics, uncertain implies uncertain is uncertain. So it's almost like uncertainty is contagious or something like that, people say. So 2 different notions of implication, 2 different operators. So we wonder, are any of these things definable in terms of one another? So again, here's our basic operators. And our first theorem is that negation is not equivalent to any formula that contains any of these other 4 operators. And the proof here is just, if we assign all the propositional values to true, then we get true from any of these. So like if you look at this little square, this corner square, it's always black. So that's different from negation, because if you feed 1 and or true into negation, you get false. So that shows that negation is undefinable in terms of all the other operators. And then our next result is that any of these operators and Lukasiewicz implication is not equivalent to any formula that uses only Kleene implication. This proof is getting a little bit longer and more computational. So it's the same basic proof method, very simple, but we used a Python program to compute the truth set algebra for the Kleene implication. So these end up being our basic truth set diagrams. So we start with P and Q. Let me find P and Q for you. So here is, oh yeah, we named them P and Q. That was smart. So here's P and here's Q. So those are basic propositions. The propositions always just have 3 values to start with, right? And then we take all the Kleene implications of them. So this is just like in alphabetical order, right? But P and Q are our starting points, our basic points. And when we combine P and Q, we get A, B, C, and E. And then, we go on from there and keep adding columns and rows until the diagram is closed under Kleene implication. I'm going to go back and let you look at all the things we can get for a second. So this is a closed set under Kleene implication. And then if we look back at our truth tables for and, or, and Lukasiewicz implication, none of them show up in this closed list. So that's an immediate proof that none of those other 3 operators are definable in terms of Kleene implication. And Yeah, we did this. You could do by hand, I guess, but you wouldn't want to. We used a Python program for it. It was quick and easy. And then here's some known equivalences in three-valued logic. So we still have De Morgan. And we kind of have Kleene implication, sort of matching, connecting with and the same way as implication does in propositional logic. And then in the Lukasiewicz implication, it's more complicated how you express and, because we got that third value that changes things. So that's what we know. Those are the formulas we know are expressible in terms of other ones, but what else? Are there other expressibilities or are they unexpressible? So our next theorem is that and is not equivalent to any formula that doesn't use negation. With your other three operators, you can't get and. So let's look at the proof for that. So when we take the closure here, we end up with 176 different truth sets, truth diagrams. So do I have, no, I don't think I even put the picture in. Yeah, so this is a big diagram. You had to use Python for this. You would not want to do this by hand, but it's still easy to check. And this is a little bit of an exhaustive search since there's only three values. It's not like we have to build up our own model and find the special propositions that give you this result. You just put in all the possibilities and you find this out. And disjunction, you got De Morgan, you've got this connection with Kleene, and we have this connection with Lukasiewicz implication, which matches with or in classical implication. So basically it's like the two implications kind of play two different roles in their connection to or. And then or is undefinable in terms of just and Kleene implication. So this is a little bit more manageable. It ends up with 36 truth sets. And then Kleene implication, wondering how it's expressible in terms of the other operators. So if you've got negation, you can write Kleene implication as other formulas. If you don't have negation, you cannot write Kleene implication as a combination of other operators. So it's unexpressible in terms of the other three operators. This one has 72 diagrams. And then Lukasiewicz implication is undefinable in terms of everything else. It's totally independent. This one, we can do exactly the same kind of proof. There's also this simpler proof, which is kind of like if you look at your truth tables, your truth diagrams, the very middle square is always an X with all these other operators, not an X with Lukasiewicz implication. And so that automatically tells us that you can't, no matter how you combine these, you're going to get X's in the middle. Lukasiewicz implication, you don't get an X in the middle. And so that's almost like a meta property of the truth set diagram for these operators. Okay, so we got a couple of minutes. I'll kind of get this wrapped up in a minute, but I'm going to talk about kind of an extension of this proof method to a countable set of diagrams. So we're going to go back to LTL, temporal logic, for a minute. So remember, FP means P is eventually true at some point in the model, some point in the future. And we're going to prove that this is not equivalent to any formula if you don't have, well, F itself, obviously, or until or weak until. So we can't define F, and we're kind of thinking of F and G as the same thing. So G is included and that's it. So you can't define F in terms of a single formula that contains X's or any Boolean combination. So intuitively, this is fairly obvious, but it's tough to prove. And so what we're going to do is we're going to consider a countable set of models. So basically, we have P and Q, and in any model, we're defining a model for the number T, and P and Q are only true at point T, no other points. Okay, so here's a picture. So here's P and Q in the T model. They're true at T, not true anywhere else. For this proof, we have to define a class of models that we kind of close under the truth sets. So alpha t is a whole set of models. It's little t. So before time little t, the formula is false. And after time big T, the formula is false. And then beta T is, and these are different kind of wild cards. So we consider all the possibilities of truth values between little t and big T. So we have a set of like 2 to the n alpha little t models, or 2 to the big T minus little t. Doesn't matter how many. And then here we have everything is true up till time little t. Consider all the possibilities for truth values between little t and big T, and then everything is true again after t plus 1. So alpha t and beta t are both sets of evaluations. P and Q are just single points. Okay, so if we consider FP, obviously FP is true from 0 up to time big T, right? And then if we look at our alpha t and beta t models, any Boolean combination of any alpha t and beta t models is going to still be an alpha t and beta t, because the only variable truth values are between little t and big T, right? In Boolean, operators can only look at the present point. They can't change the past or the future. So, and if we have any temporal formula whose truth value is in alpha t or in beta t, so it only changes the truth values between little t and big T, then if we look at x phi, x of that formula, remember x is the next step operator that just looks at one step in the future, it can change one more truth value. So its model then, its truth set is going to be an alpha t minus 1 union beta t minus 1, where the truth values are variable between little t minus 1 and big T. So we're kind of like adding one step of variability to our window of what can have different truth values. Okay, so then let's say, this is a little bit of a proof by contradiction. If we had a formula that expressed FP in terms of X, it would have to have a certain number of X's, right? A fixed number of X's. So we'll call it K occurrence of X's. So it can only modify up to like big T minus K truth values. So the T truth value is coming from it being built up of P and Q, and then each X you add adds one more step of the model that it can have variable truth values at. So you end up seeing the truth set for phi has to be in alpha big T minus K or beta big T minus K. Everything else has to be either true or false, no variation. So then, our actual theorem is that shows us that FP, which is definitely not in alpha T or beta T because it has stuff true at the beginning and then false in the final future. Not in alpha T or beta T because in alpha T and beta T, like the beginning and the eventual future match either true or false. So F is not expressible in terms of X modalities. So that proof fits into that same system. And that's not a new result, but the other proofs of that are more complicated. Okay. Yeah, so that's it for today. I just wanted to show you this truth set closure method with truth set algebras to prove undefinability results. And we did use this to prove a bunch of new results with our kind of AI memory focused logic, but that's a whole other topic and a whole talk to just go through that logic. Here are the papers where some of these results were proved before using different methods. But we kind of unified all of these results. So that's it for today. Thank you very much for coming to this talk.
Thank you very much, Sophia. Interesting talk, interesting method. Questions?
Yes, Sophia, I have a question. I'm not expert in logic at all, but you say you apply your technique to classical logic systems. So, what would you mean, or what you can explain to the non-experts? What is a modern logical system?
Oh, a modern logical system? Like something that's interesting for problems that people are working on now? Is that what you mean?
Right.
Yeah, okay, so modern logical systems, well, I'll just talk about like what I know and what I work on. I think modern logical systems that are interesting are systems that include multiple agents, right? Where each agent has access to their own information. So that kind of brings knowledge into the picture, right? And then especially interesting is multi-agent logics where agents can make decisions based on their own knowledge. So if you have a model and it has a bunch of states and a bunch of agents, and each agent only has access to certain information in each state, that's going to affect the decisions that agents can make if the model is dynamic and updates according to agents' actions. So you could think of this like a really simple example would be something like if you have robots and one robot has vision, a different robot has hearing. And so the vision agent can make their own decisions based on like what they see. The hearing robot can make their own decisions based on what they hear. And if the robots are trying to communicate to maybe reach a goal, like reach a certain state, whether they could achieve that state or not. So that's a little bit of the kind of system that we were developing when we came up with this method of definability. And so our modalities, our operators were like, this goal is achievable if the agents have perfect memory. This goal is achievable if the agents have imperfect memory. Maybe they don't have any memory. They only remember 3 states, something like that. This goal is achievable if the agents cooperate. This goal is achievable if the agents don't cooperate. They just each take their own action. So that's a kind of modern logic that's interesting. And then obviously it's interesting to be able to say something like, if the agents have memory and they cooperate, you can express the goals that they can achieve in terms of agents without memory who still cooperate, something like that. That actually would not normally be true, right? But if you can say something like that, it's very interesting. So those are modern logics. That's the kind of logic we were working on when we came up with this truth set method. Does that make sense? Is that what you were asking?
Sure. Thank you very much.
Good.
Are there any more questions? I have a
Excuse
question.
me.
Yeah, sorry. Yeah, go ahead. Sorry.
Don't worry. Excuse me, Sophia. Do you work with other logics? For example, very consistent logic or other, or linear, or I don't know.
I haven't worked with definability and paraconsistent logic, but I'm definitely interested in paraconsistent logic. I've been kind of thinking about its applications to social networks. So paraconsistent logic is a logic where rather than just true and false, you have like a whole spectrum of possible truth values. And I think that would be super applicable to social networks. That's another multi-agent system where agents have different information and make different decisions, right? Because in a social network, normally people don't just have like, this is true and this is false, but they have something they strongly believe, something they like slightly believe, something they think is implausible. So they have a whole range of beliefs. So yeah, I haven't really worked with paraconsistent logic, but I have been trying to learn about it. Because to me, it looks really interesting and important for more like human-centered applications that aren't just true and false, but you have a spectrum of belief or a spectrum of plausibility, something like that, that's not exactly probabilistic, but still this range of values.
Thank you.
Thank you.
I can see your reference, please.
Let's see.
The other reference. Thank you very much.
Yeah, you're welcome. And yeah, we haven't published this paper yet. It's gotten rejected a few places because it's kind of a weird topic, I think, like new proofs of old results. But we do have an archive paper on this if anybody's interested in looking at that. it's on archive. It's me and Pavel and a couple of Pavel's students.
Great. More questions? I do have a question. Have you thought about kind of the limits of your method? Because you started with, let's say, with a kind of simple version, I will say. And then in the last application, it was more complex, right? This kind of argument is more difficult. But have you ever thought about some cases that you can imagine that you will not be able to handle this way?
You mean like computationally, or just like this method wouldn't apply to?
Yeah, just the method, not computationally, just the method
Oh,
itself.
yeah.
That you.
Yeah, we have sort of been thinking about that. Like, there are a lot of times people use bisimulation to prove this kind of undefinability result, right? So they'll show that two systems, if they're bisimilar, then they satisfy all the same formulas in in one logic, sorry. And then they'll show that there's another logic that can distinguish between these two bisimilar systems. And so that's a way of proving that one logic is undefinable in terms of another. So we were looking at whether we can directly translate bisimulation methods into truth set algebras, kind of like in a uniform way, or whether it's sort of like a case-by-case thing and maybe it sometimes doesn't work. Yeah. So yeah, that's a good question. Like, how general is this? And is this always applicable, or is it only applicable to some logics? We've been kind of excited about how general it seems to be so far. So far, like, we've tried it on several different logics and it's always worked well. So.
Yeah. Okay, great. Very nice.
Yeah.
So if are there any question? Is there any question? So if not, thank you very much, Sophia. Very nice talk, very interesting. And yeah, thanks.
Yeah, thank you.